All right, everybody. At this point, we've done some basic calculations of approximating areas under the curves using left-hand rectangular method, right-hand rectangular method, and midpoint rectangular method. There will be one more method coming called the trapezoid method down the road. That'll give sometimes an even better approximation. But what we would like to do today is to connect the approximations that we're doing with areas under the curve into a summation notation that sums up the areas of those rectangles. And ultimately, how do we actually then calculate the complete or exact area under the curve? And that's going to bring in something called the definite integral, which you might have heard talking to other people in the class. So we've got a lot ahead here, so grab your notebook, where, as always, you can pause in what we're doing, the video, when I might ask you to practice a problem, and have your graphing calculator ready too. We're going to take a couple notes in our notebook here. So let's get all right, so a quick little review from what we did before. So we found areas under the curve by making little rectangles. We had subintervals, which were a width between two values of the left and the right-hand endpoints of my rectangles. These are called Riemann or Riemann sums, and the mathematician Bernard Riemann. Got a link on my Canvas page if you'd like to find out more about him. But the whole interval itself is called a partition, and then each little subinterval, and we had talked about, again, as the more subintervals that you make, the narrower they're going to be, and then so your rectangles would be smaller and skinnier, and the more rectangles you can fill in, the more accurate your approximation is going to be. Ultimately, our goal is to get an infinite number of rectangles underneath of there. So how do we, the proper notation here? So the width of my individual intervals, or delta x, that is going to be the width of my subintervals, is a basic calculation of the difference of the endpoints, a, b minus a, divided by the number of subintervals. N is the number of subintervals. So again, the more subintervals you have, the skinnier your rectangles are going to be. So that's the width of each of my rectangles. That's delta x. And the heights themselves were determined by function values, the value of the function at a particular point. So in this summation notation down here, we have the width is delta x, and the height is the function. So the height times the width gives me the area of the rectangle, and I'm going to sum up from I equals 1 to n. I is just like a counter, like the first subinterval, the second subinterval, and this works for if we were doing left, right, or even midpoint. But my goal is to then go from I equals 1 up to n, but ultimately I would like to make the number of subintervals approach an infinite number of subintervals. Because the more subintervals that I have, the skinnier the rectangles. So this is calculating the area of one of the rectangles, and then I'm going to sum up an infinite number of them. So this kind of looks like a little bit of a clunky notation. So one of our founders of calculus, Leibniz, cleared that up with a prettier notation. So here is my summation notation of how to sum up an infinite number of rectangles. And what he came up with was the integral symbol. This looks like a big curvy S for sum. And it's representing that I'm going to find the area under the curve, the function f of x, with little widths of dx. dx that is representing those little small changes in delta x. We'll talk about that differential later on more specifically. And obviously my interval is going from a to b. This is called the definite integral because I'm going from a definite value from a to b. And again, this is giving me the area under the curve. In fact, this is giving me the exact area under the curve because I'm going to do an infinite number of rectangles. What we don't have right now is a methodology for how to actually manipulate the function and get this number. How do I actually get the area? All we know is approximations with LRAMs, RRAMs, and MRAMs. But now we have a notation to represent the exact area under the curve if I was looking to find it. All right. So just a little notation about the notation. My lower limit of integration is a. My upper limit of integration is b. Always read from left to right, the lower number to the upper number. The upper number should be the value that is greater than the lower number. Not always, but typically. My integration symbol is the big curvy S. Integrand is the function that I'm that I'm integrating, I should say. And then the dx, that x is playing an important role. That's telling me actually the variable of integration, which will play a role a little bit down the road now. But for now, we should basically think of, again, this notation, is giving me the height times the width of my rectangles. Okay, so again, we've got this notation to represent the exact area under the curve. We've got ways to approximate them, but I don't know how to evaluate this and get the exact area. So let's take a look at a physics example. This is the one that we saw before. So before we, again, said that if I have a velocity time function, then the area underneath of that velocity time function is giving me my displacement, or my distance traveled. So in this case, it was a constant of 3. 3 feet per second was my velocity over an interval of 4 seconds. Seconds cancel out and tell me, okay, I've traveled 12 feet. That's my displacement. No change in direction for this problem. Okay, so we understand area under the curve represents my displacements traveled. So, okay, what about if I don't have a constant velocity? So I know I can go from a velocity equation back to a position equation, so I can maybe calculate some distance traveled like we did much earlier. Now, if you remember before, so I'm going to anti-differentiate. So antiderivative of 1/2 t. What function has a derivative of 1/2 t? Well, it's going to be 1/4 t squared, and you can check it by differentiating. And then what function has a derivative of 1? Well, if I go backwards, the function is going to be just t. Now, hopefully you remember I typically also add a plus c, but we're going to assume that c is going to be 0 because I'm going to start my initial position at time 0 to be position 0. So to make life easier for us right now, that's just going to be 0. So I have a position equation, and we've done this before. We've taken that position equation and found the displacement during different intervals, and when you wanted to find the total distance, you had to separate it out into 2 different intervals, one where you're moving forward and one where you're moving backwards. So this isn't new. We're just now going to connect what we've been doing before. So now that I have my position equation, I can find my position at time 4 seconds at the very end by substituting in 4 into that equation, and I wind up getting 8. Now, my position at time 0 is 0, so my displacement is a total of 8. So I know, based upon anti-differentiation, that my position is 8, or the distance that I traveled was also 8. Well, now what if I find the area underneath this graph? Well, the area of a trapezoid is 1/2 the sum of the bases times the height. Now, the bases are these sides coming up here, base 1, base 2, and the height is the whole width this way. So here's my trapezoid kind of laying on its side. So 1/2 sum of the bases, this has a height of 1, this has a height of 3, and the whole height of the trapezoid is 4, and that also comes out to be 8. So what are we seeing here? Well, we're seeing that the area under the curve, which we could do through simple geometry, we didn't have to do approximations here, the area under the curve is exactly the same as our process of anti-differentiation from going from velocity back to position. So antiderivatives might be helpful to us in doing our calculations of exact area under the curve. So what if I have this function? This should seem familiar. We did this, the one before, 1/8 t squared plus 1. I could split it up into a whole bunch of different trapezoids, which we'll do later. But then the area underneath of that curve is also going to represent the total distance traveled. So let's take this velocity equation, and I'm going to anti-differentiate it. So the antiderivative, and I know we're going to practice this a little bit more, what you could think of is, okay, I'm going to leave the 1/8 alone. What's the antiderivative of t squared? What function has a derivative of t squared? Well, I know it's going to have to go up to t cubed, but I'm going to need a 1/3 there, because if I differentiate it, I need those 3's to cancel out. That's where my 1/24 t cubed is coming from. Antiderivative of 1 obviously just becomes just t. Again, we could do a plus c, but we'll assume that at position 0 or at time 0. So here's my position. At time 4, I can figure out that my position is, or my displacement is going to be 6 2/3. So I can say that the area underneath of that curve is 6 2/3 through anti-differentiation. Slide here and just show what we wound up doing. We took, and we could say that the integral of 1/8 t squared plus 1 dt from 0 to 4, we took its antiderivative, which was 1/24 t cubed plus t from 0 to 4, and then we substituted in 4, and that's how I got my 6 2/3, and I would then substitute in 0, but that's position 0, so therefore the position and my displacement are the same thing. So that's the notation of what we just did. You can pause here if you're catching up. All right, so let's kind of summarize where we're at this point. We started in with actually, let me go back. So here's what we did. We went from our summation notation to our integral notation. And then what we did is we took the antiderivative. Capital F is what we're going to name as the antiderivative of lowercase f. So we took the antiderivative and we evaluated it at the upper limit, which was 4, minus the lower limit. That would have been 0, but the position at 0 was 0, to get my value. So in essence, if I'm trying to find the area underneath of a curve, I can set up a definite integral and find the difference of the antiderivatives to find the exact area under the curve. And we've proved that through the use of our physics example in velocity versus displacement, which we're going to do a lot in this course. All right, so let's put this into action. And again, you can pause me to kind of catch up here. All right, so I want to find the area underneath the curve from 1 to 2. All right, so here's my integral notation. The first thing I'm going to do is I'm going to anti-differentiate it. And I'm going to antiderivative of x cubed, x squared is 1/3 x cubed. And remember, you can always check this by differentiating. And that's going to go from 1 to 2. We use this vertical bar to show what my limits of the entire interval are. And then I'm going to figure out, okay, we can think of this as if this was a velocity equation, then this is going to be my position equation, the antiderivative. Well, how do I find the total distance traveled, which would represent the area under the curve? Well, I'm going to find my position at time 2 minus my position at time 1. And this should seem extremely familiar from what we did before. And then so it's the antiderivative at the upper limit of 2 minus the antiderivative at the lower limit of 2. So what do I get? 4/3. Oh, wait a second. This is, I can't even see. This is cubed. So 8/3 minus 1/3. And so I come out to be 7/3. And it's really that simple. 7/3 is the exact area underneath of this curve from 1 to 2 using antiderivatives. So again, we can approximate these through Riemann sums, left, right, and midpoint approximations, but now we have a way of actually finding the exact area under the curve. Pretty cool, huh? All right, let's do another famous one here. How about the sine function from 0 to pi? All right, so I would like to know, what is this exact area underneath of the sine function from 0 to pi? Now, if I imagine a little rectangle here to try to approximate what it would be, the area of that rectangle is pi. It's 1 tall and pi wide. So I know the answer is going to have to be less than pi. So any kind of guesses? All right, let's set up our definite integral. All right, this notation saying I'm about to find the area under the curve from 0 to pi. And again, we use antiderivatives. What's the antiderivative of sine? That's going to be negative cosine from 0 to pi. And then I'm going to substitute in my upper limit minus my lower limit. Okay, cosine of pi, I might need to, if you need to. So here's pi, here's 2 pi, here's my cosine function. So let's see, what do I got? Cosine of pi is -1. Cosine of 0 is 1. And it looks like, look at that. Holy schmoly. It's exactly 2 squared units. Would you ever have thought that? That exact area underneath of one hump of a regular sine function, period of 2 pi and an amplitude of 1, that is just 2 squared units. Exactly 2 squared units. Exactly 2. So that's pretty awesome. And look how simple and elegant this was to actually calculate. So from an antiderivative and the difference of antiderivatives, I get that value. Boy, I love this. All right, so let's take a look at this one. Area enclosed by -x squared plus 4 in the x-axis. Notice I'm not giving us an interval. So I'm going to have to actually, it's an upside-down parabola, shift it up 4. So for some of these problems, you're going to have to do a little bit of figuring out. I need to figure out what these intercepts are, and how do I find the intercepts? Well, those are the zeros of the function, so I set my function equal to 0. And I don't think it would take much work to see that it's going to be plus or minus 2. So I'm going to be integrating from -2 to 2 of -x squared plus 4 dx. So again, function represents the height, dx represents the width of the little rectangles, and I'm doing an infinite number of rectangles here. So the first thing I got to do is an antiderivative. So -1/3 x cubed. We've done that a couple times here. What's the antiderivative of 4? What function has a derivative of 4? And it's going to be 4x from -2 to 2. And so now, always start with the upper limit of integration. So the 2 goes in first. Oops, that's cubed. Plus 4 times 2. Minus the lower limit of integration, substituted into the antiderivative. Again, this should seem extremely familiar from what we did for total distance problems in the past. All right, I don't care what this answer is. I'm going to stop right here. That's good enough for my solution. Now, if this was multiple choice, yeah, you'd have to keep going. But for now, I'm good with this. The whole point of this is that you had to find the interval itself. All right, let's keep going. A little bit more to chat about here. So now, let's see maybe how our graphing calculator can do this. Because as you can see, a little snapshot of my graphing calculator, it actually shows it calculating an area underneath of the graph. And I'll show you that here in a minute. All right, so let's go back to this other problem before, the 7/3 answer that I got underneath of here a minute ago. So there's 2 ways to do this on your graphing calculator. One way is a numerical way, which will just give you the numerical value of the area under the curve. And for that, you need to go to the Math 9 on the newer calculators, and you should see FNINT. Actually, most calculators, it might be number 9. FNINT. Now, the newer calculators will bring up this integral notation, and you just literally substitute in lower limit, upper limit, integrand of x squared, and then the variable of integration, you got to put in a variable of x there. You use that x button that you do all the time. And there it is. Hit enter, and it gives you 7/3. You can even have your calculator change it to a fraction. Older calculators, it'll bring up FNINT, and then you have to put in 4 inputs separated by commas. The commas above the 7 button. So you got to put in the function, comma x, which represents the variable of integration, the lower limit first, which is going to be 1 in this case, and then the upper limit, which is 2. Hit enter on that, and it'll give you 7/3. So if you have an older calculator, you're going to have to use this notation and just substitute it. It won't look like this, but it'll still calculate. You have to be able to do this on the AP exam. There are problems on the AP exam that require you to calculate this where you can't calculate it by hand. So this is definitely something we're going to want to practice. The second way is to graphical method. And if you graph the function, in this case it was x squared. So graph x squared, and then go into the place where you always want to do some calculations on your graph, which is second graph, which is above trace. And if you go into there, you'll see number 7 is an integral. So second calc is the integral. And so it's going to ask you a lower bound, which will be 1, and an upper bound, which will be 2, and hit enter, and all the calculators, regardless of the model, will shade in that little area and then give you the approximation down at the bottom, which will be 2.33333 or 7/3. So make sure you practice with both of these methods, both from the home screen underneath the math menu and graphing underneath Second Calc. I will tell you, most of the time, we're going to do number 1. We won't necessarily care what the graph looks like. In fact, sometimes we'd have to play around with the window too much. So practice with number 1, which is a Math 9. All right, something to keep in mind here is that what happens when the function maybe dips below the x-axis, which we've dealt before, or the horizontal axis, I should say. We've dealt with that before in our total distance problems. If the function changes directions, then the velocity is going to go from above the curve, x-axis, to below. So if I want total distance, I'm going to have to separate out the intervals, which is what you've done in the past. Well, we've got to do that with the integrals as well. Because if I integrate all the way from 0 to, in this case, 3 pi over 2, it is going to cancel out any of the little rectangles that were technically above. Remember, there's an infinite number of them. With rectangles that are below, because these rectangles have negative heights, because their function values would be negatives. So there might be a time if all I want is displacement, yeah, part of these areas are going to cancel each other out, and that's fine. But if I want the total distance or the total area, then I'm going to have to separate out my integral. So I have one integral for going from 0 to pi over 2. I have another integral going from pi over 2 to 3 pi over 2. And since that one is going to return me negative values, I am going to subtract those negative values. The other way to approach this is by adding and then taking the absolute value. And we'll talk about that here in a second. But otherwise, we're separating and then figuring them out separately, which is, again, like we've been doing before. You can pause here and then kind of follow what I'm going to do here. I'm just going to talk very briefly because it's pretty straightforward. Antiderivative for each of them. Substitute in the upper limit first and the lower limit second. Find each one individually. So from here I can see, okay, then this area right here must have had an area of 1, which makes sense because it's half of that hump that, remember, we saw before the area was 2. And this is a full hump underneath of the horizontal axis, which came out to be -2 for that area. But again, remember, I want total distance, so I'm going to subtract that -2 or take its absolute value and get a total of 3. 3 would be the total area bounded by this function and the horizontal axis. All right, quick little practice doing some of these by hand. Again, I'm going to go through these kind of quick, but you can always pause. So let's do these by hand, and then you can check them on your calculator with a Math 9. But in this case, antiderivative from 1 to 3, upper limit in first, so putting the 3's in first, minus, always subtraction, putting in the lower ones, and then evaluating, and I get 14. Antiderivative of 5 over x. What function has a derivative of 5 over x? Well, if you're careful, remember it's 5 ln of x. The derivative of the natural log of x is 1 over x. Yeah, we're going to have to start brushing off some cobwebs. So 5 ln of 2 minus, 5 ln of 1. Natural log of 1 is 0. So my final answer would be 5 ln of 2. Again, pause me as I'm going here so you can give these a try. So in this case, whatever 27 plus 9 halves is. Ooh, fun one here. Remember, derivative of tangent is secant squared. It's been a little while. going to start pulling out all these old ones. And the tangent of 90 degrees is 1. The tangent of 0 is 0. So I get a big fat 1. All right. Staying with me here, almost here to the end. This is a lot here. All right, so a velocity function, let's put it in the context. On the interval from 0 to 6, I want to set up, using definite integrals, the displacement and the total distance. So my displacement will simply be the integral from 0 to 6 of t squared minus 4t plus 4. Now, I'm going to use my calculator and do that on my calculator, and you should too, and I get 24. Now, the total distance, remember, what I would have to do is first figure out where this function hits 0, and then separate out into separate intervals. But if I'm going to use my calculator, I'm going to cheat a little bit here. So let's say that part of the graph did dip below. Well, I would want that part that's below to be maybe reflected up above so I can just integrate the whole thing. Well, how do I reflect graphs up above so everything's positive? Well, I'm going to use absolute values. So when you go to do this one on your calculator, you're going to do a math 9, but then you're going to bring in the absolute value of the function. And remember, that's underneath the math and then number submenu. Do that and see what you get. Well, I get 24, which tells me that apparently this particle didn't change direction during the interval from 0 to 6. The displacement and the total distance were exactly the same. There was no change in direction. This graph didn't dip below the horizontal axis on that interval. All right, find the total area bounded between this function and the x-axis on 0 to 5. So I've already graphed this. So we're going to set this up two different ways, and we can let our calculator do it. But I'm going to set it first up with my little shortcut way, is that if I want that total area, I can just use the absolute value, because clearly I can see it's crossing the x-axis right there at 1. That would give me the total area, which would include this, and 1, 2, 3, 4, 5, all the way down to here. Total area. That wouldn't be canceling out those areas. If I was doing this by hand, I'd have to first integrate from 0 to 1 of negative 2x plus 2. Then I'd have to integrate from 1 to 5 of negative 2x plus 2. And since this second one is going to turn out to be a negative area because it's below, I'm going to subtract that negative area. So both of these wind up representing the same total area, and in the end, I get an answer that's about 17. I think it was 16.999999. All right, one more. Now, in this case, looking at the graph, I really can't tell. I mean, I could use my calculator and find the x-intercepts. I guess I only need the one from 0 to 3. I'm not going into those negatives. So I could use second calc and then enter 0 and find what that 0 is. But again, if I'm using my graphing calculator to evaluate this, which you will be doing, I want this total area from 0 all the way down here to 1, 2, 3, all of that area. I can just simply use an absolute value. And in the end, I get about 23.314. All right, that's a lot. But we've now kind of crossed the threshold into going from approximations of areas under the curve to exact areas under the curve using anti-differentiation and the use of the definite integral. All right, make sure you check Canvas to see what I want you to do next.